So now we have a little bit more complicated circuit, but I think the math for this one actually turns out to be a little bit easier. So now we have two batteries in this circuit. We've got a battery right here, which I'm calling supplying an EMF V2, and I have another battery up here supplying an EMF of V1. And then I've chosen a particular direction for the current, which I'm telling you. I'm going to call current I1 that's running through this branch right here. And when it reaches this junction, I'm going to call I2 the current that runs off in this direction, I3 the current that runs off in this direction. So again, we're going to find three equations. We've got three unknowns, which are the three currents. In order to solve this equation, we're going to start with our first equation, which is from Kirchhoff's first rule, the junction rule, and then we're going to use the other two equations coming from Kirchhoff's second rule, which is the loop rule. And so we can create one loop within this section of the circuit, and we can create another loop through this section of the circuit.
Okay, so now we're going to use circuit analysis again and Kirchhoff's two rules in order to help us solve this circuit. Now this circuit is interesting because it has two batteries inside it instead of one. And with these two batteries, it's a lot harder to solve this problem using just sort of logic and piecing together all the currents flowing through the individual resistors and the potential differences across the individual resistors. We really need to use Kirchhoff's rules in order to help us solve this problem here. Now, I've drawn in a convention for the currents. I'm going to say that the current flowing through this central wire here is I1 and is flowing to the right, and then it reaches this branch and it branches off into I3, which I'm saying is going to go around this way, and I2, which I say is going to go up and this way. So now we've taken care of our junction rule. Let's draw in our Kirchhoff loops in order to get us our second and third equations. So for loop 1, I'm going to start here by going from the negative to the positive terminal of this battery right here, and I'm going to go around in this direction, okay? And so I'm going to go, let's see, that's counterclockwise around that first loop. That's loop 1. And for my second loop, I'm going to go clockwise through here. And we see that for my second loop, loop 2, and loop 1, they both align in the same direction here with my current direction that I chose for I1. Now, if I look at loop 1 and I write down my equation for Kirchhoff's second rule, it shows that the sum of all of the potential differences along my loop must be 0. And so if I start here with loop 1 and I start with the battery V2 that I'm going through, I'm going from negative to positive terminal of my battery. And so if I write down the equation for loop 1 here, going along with my Kirchhoff's rules, then my Kirchhoff's loop rule, I will be going from negative to positive terminal through V2. So I'm going to write this as V2, okay? And then in the direction of the current, I'm going through resistor 2. So minus, because we're losing potential as we go with the current through the resistor, minus I1 R2. So this is the potential difference that we lose or decrease as we go across this resistor. So we've got current, which we called I1, moving through this resistor, but that's resistor 2. So I'm going to say minus I1 R2. And then along the loop, I'm going to go through the other battery. I'm going from the negative to positive terminal. And so that's a positive or an increase in my potential. So I'm going to call that positive V1, where I've labeled V2 and V1 as the EMFs of the batteries that we're using. And then I go through, along this loop, I go through resistor 1. And so that will be minus I2 R1. I2, because the current going all along this loop from here over to down here, that current we've labeled as I2. So that will be minus I2 R1 that all equals 0. So that's my second equation. Let me double check. There we go. That's correct. And then for loop 2, I've got my final equation. If we look at loop 2, this one's a little bit less complicated. We're starting at our EMF, right here, our battery EMF, which has a positive 10 volts. So we'll call that V2. We're going from negative to positive into that terminal around my loop. So that's an increase in my potential, so positive value. And then I move through with that loop my resistor 2 with current I1. So minus I1 R2. And then along that loop, I'm also going through resistor 3 with current 3. And so that's going to be minus I1 R3. So the potential that we lose across that resistor there is minus I3 R3. And that all has to equal 0. So that is equation 3. So we've got 3 equations, 3 unknowns. We're going to use these in a combination in order to solve for the currents running through our system. So just like we did in the other problems, I'm going to tell you right now that instead of solving these equations algebraically, let's go ahead and just plug in the values that they should be. So if I start with equation 2 here, I'm going to have V2 was 10 volts minus R2 is 6 ohms, so minus 6I1, plus V1 is 14 volts plus 14 minus, through my first resistor, we have 4 ohms, so minus 4I2, and that all equals 0, okay? And what I'm going to do right now is I'm going to go ahead and solve this equation for I2. So if I solve this equation for I2, I'm going to add this term, minus 4I2, I'm going to add it to the other side, and then I'm going to divide the whole thing by 4, okay? So, well, let's just start by adding 4I2 to the other side. So we have 4I2 equals, add 4I2 to the other side, I've got 10 plus 14, so that's 24 minus 6I1, okay? And then I have to divide both sides by 4, and so then if I do that, I get that I2 is equal to 6 minus 1.5I1. And I'm going to call that equation 4. All right, so now let's go over here and work with our equation 3 and stick in those values. So our EMF for V2 is 10 volts minus the resistance on R2 is 6 ohms. So this is going to be minus 6I1 minus resistor 3 is 2 ohms, so minus 2I3, and that all equals 0. Okay. So now I'm going to solve this equation for I3, right? And if I do that, I'm going to add 2I3 to the other side. So I have 2I3 is equal to 10 minus 6I1. Divide both sides by 2. I3 is equal to 5 minus 3I1. And that's equation 5. Okay. So I did it that way because we see I have our first equation, I1 is equal to I2 plus I3. For equation 4, right here, I have I2 in terms of I1. For equation 5, I have I3 in terms of I1. And so what I can do now is take equation 4 and equation 5 and substitute them back in to my junction equation. And then the only variable that I'll have in that equation that I need to solve for is I1. And so if I start over here with this one, then I have that I1 is equal to, for I2, I've got 6 minus 1.5 I1. And then I3 would be plus 5 minus 3 I1. Okay? So I1 is equal to all these terms together. So if I combine like terms, I've got 6 plus 5, so that's 11. So I1 is equal to 11, and I have minus 1.5 I1 minus 3 I1. And so that's going to be minus 4.5 I1. I1 is equal to 11 minus 4.5 I1. So now I have to combine both of my terms that have I1 in it. So this is really just 1 I1. So if I add 4.5 I1 to both sides, then I have that, so 1 plus 4.5, that's 5.5. I1 is equal to 11. Now I divide both sides by 5.5, and then I1 is equal to 11 divided by 5.5, which is 2.0 amperes. Yeah, 2 amperes. So I1 is equal to 2 amperes. And that's where we were going with that problem. But let's keep on going. We've got I1. We've got equations 4 and 5. So let's just go ahead and plug I1 in there to see what I2 and I3 should be. Okay. So if I do that, let's start with, yeah, this is good. So we've got 6 minus 1.5 I1 was 2 amperes. So that's equal to 6 minus 3. And so that equals 3 amperes for I2. Okay? I2 is 3 amperes. And then I3. I3 is equal to 5 minus 3 times 2. Okay. So we've got 5 minus 6. I3 is equal to minus 1 ampere. Okay, what does that mean? So in the end, we found here that actually I3 is negative. I3 is equal to minus 1 ampere. So what does it mean when we have a negative current? Well, that just means that we chose the convention for our current in the first place to be in the wrong direction. That's okay though. The amplitude or the magnitude of I3 is still positive 1 amperes. And so if I were to come over here back to my junction, and instead, if I were to draw in the direction that I3 should be going, upward instead of downward, I'll find that I1 plus I3 should give me I2. So if I say 2 amperes plus 1 amperes should equal I2, which we found to be 3 amperes. So that's okay. It still works out mathematically to have the equation written like this. If I say I1 is 2 amperes, that equals I2 plus I3. If I2 is 3, I1 is negative 1, then we still get 2 and 2 on both sides. So if you're doing a problem like this and you happen to accidentally choose at your junction one of the currents or two of the currents to be moving in the wrong direction, that's fine. So if you've done all the work here correctly, if you end up getting a negative sign in the end for one of your currents, that just means you chose the initial conventional direction for that current of the wrong sign. And what I'd also suggest to you, especially since some of these circuits can be really complicated, is to take the circuit that we've set up right here and set it up inside the FET circuit analysis labs that we've been working through. And if you set them up there and you click to show the direction of the conventional current, you will indeed find that our current I3 should be pointing upward in this direction. I1 will be moving off to the right, and then I2 will also be pointing upward.